And bonds. All right, so this lesson is going to require some previous knowledge of hydrocarbons. So alkanes, alkenes, alkynes, some expectation that you've already done some work with that. Additionally, we're going to talk about combustion, addition, and substitution reactions. And since we're familiar with a lot of drawings, there's a few other molecules we need to cover first, because these 10 molecules I'm about to show you will appear frequently throughout this lesson, in addition to all the hydrocarbons that we've been learning about. So if you want to just make a little table here, the very first one and the most simple molecule that we need to talk about is hydrogen gas. It's in group 1. It shares one valence electron, and so it ends up having a single bond. Now there's a bunch of gases in group 7, including fluorine, that, they're in group 7, they share one, so they're going to have singular bonds. So the rest of these gases in group 7, so chlorine, single bond, bromine, single bond, and iodine, single bond, all these gases are all going to bond in the same way. So all 5 of the gases on this slide all have single bonds. As we move on, though, they get a little more complex. So we've got oxygen gas. Oxygen's in group 6. It'll share 2 valence electrons to get up to 8, and thus we have a double bond for oxygen gas. Nitrogen gas is in group 5. It'll share 3, so nitrogen gas ends up with a triple bond. Water is a molecule that's going to appear frequently. It's made up of 2 OH bonds, so 2 per molecule. Another common one is ammonia gas, NH3, and this one has all single bonds as well. And lastly, carbon dioxide, and this one has a couple of double bonds. So now that you have all of these written down, they're going to appear throughout our lesson, and the expectation is you can take a look back at this, memorize the bonds, and there you go. That's really what you're going to have to do, is commit these things to memory. So we're going to talk about some exothermic and endothermic reactions here. So during a chemical reaction, the chemical bonds and the reactants are broken and new bonds are formed. So the breaking of bonds requires energy, while the creation of bonds releases energy. So really it's a 2-step process. We've got the energy that's released when we break bonds, and then the second step is the energy needed to create new bonds. So there's 2 steps here. For a chemical reaction like the one described, the total energy in the system and the surroundings must be the same, so there's really no net change. This means that the energy must either enter the system from the surroundings or exit the system into the surroundings, and this is where exothermic and endothermic, so exothermic is hot and endothermic is cold, this is where these come into play. So system could be anything like, say, a test tube where you're doing the reaction, and then in which case the surroundings would be the rest of the world. So 2 things are going to happen. Either your system is going to get hot or your system is going to get cold. And we're going to take a look at those 2 scenarios with energy now. So a reaction that produces an excess of heat or thermal energy is known as an exothermic reaction. Heat exits the system. Exit, exit. So in this case, it would feel hot. So this is because the energy required to break the bonds and the reactants is less than the energy produced by product formation. I'm going to show you a picture in a second to better illustrate this. In fact, here it is. So we've got an axis, we've got potential energy, and we've got time. So we've got some reactants in our test tube, and the very first thing that's going to happen, step 1, is that the bonds are going to break and the overall energy in our system increases. A little bit of time is going to pass. Step 2 is going to occur, and that's where bonds are going to form, and we end up with our products here. So if we just consider this to be our system, we actually have less energy in the system. So we started here and we're ending up here now. We have a difference. We have less energy in our system. So we've got a change in energy. Energy in the system has gone down. And this is what is represented by an exothermic reaction. So this change in energy you feel as heat coming off of the reaction. So energy is released into the surroundings from the system. An endothermic reaction is completely backwards, or opposite, I should say. We have the same graph, if you will. We have our reactants. That's all the same. We break bonds. We reform bonds, except this time our products are higher up. We have more energy in the system. We started here. If you want, you could assign any number to this. Say it's 100, and now we're up at products. Say that's 150. We've increased in energy. We have a change in energy that is increased. Now, when you probably think that, you're hearing, oh, increase, it gets hot. No, this is, again, we are talking about a system here. And what's happened to the system is it's actually taken in energy or heat from the surroundings. That's how this has gone up. It's taken in energy. And when it takes in energy, we feel that as being cold because we are in the surroundings. So there's a quick breakdown of endothermic and exothermic reactions. Now we're going to talk a little bit about delta H, and it's a measure of this total internal energy of a substance during a chemical reaction. The bonds and the reactants must break first, and for bonds to be broken, energy must be added, which is in fact an endothermic process, right? And we just talked about that on the last slide. We feel energy as cold. We feel cold in that situation. This results in energy term having a positive sign. So we're going to have to associate endothermic reactions with a positive delta H. When we make bonds, when we make new bonds, this releases energy, which is an exothermic process. So whenever we release energy, releasing gets hot. Thus, the energy term associated with the step is negative because the system has lost heat. That's where the negative is coming from. So what we're going to do here is we're going to take our delta H and we're going to take the sum of the energy required to break the old bonds. We're going to find these values on a table I'm about to show you. And we're going to subtract off the sum of the energy released in the formation of the new bonds. And there's probably a simpler way to write this. This is our energy required subtracted by our energy released. Now here's the table I mentioned. I will try to link this through Google Docs in the description. If not, here it is. These are the values I'm going to be using. You can always Google them. They should be approximately the same. We've got it broken down into elements, and then we've got kilojoules per mole here for each of these terms. Notice down here we have some multi-bonds. We'll be using lots of those ones as well. So let's apply these to a question. So I want you to prove the combustion of pentane is exothermic. We know combustion is always exothermic, so what I want to do here is I want to prove it mathematically. So first thing we're going to need to do is remember that our combustion equation is a fuel, which is going to be our hydrocarbon. It's going to be our pentane. We add that to oxygen gas. In the presence of oxygen gas, we're going to make water, carbon dioxide, and we're going to numerically figure out what the energy term is. It should be on this side. So first things first is we write the formula of pentane. If you're not sure the formula of pentane, draw pentane out. Count up how many hydrogens, etc., and carbons there are. And then you can just write that formula down there. So C5H12. Once we have that, we're going to need to balance this equation. There's a quick balance. Next step is we're going to need to draw out all these molecules. I know I already talked about drawing pentane. Well, there it is again. So I've drawn out pentane. Now, I'm going to have to draw out 8 oxygen gases. Remember early on, we drew oxygen with a double bond. So we have 8 of these double bonded oxygens to deal with. Those are going to represent our reactants, right? Reactants are on the left side of our arrow. All right, and on the other side, we're going to have our products. So our products are made up of 6 H2Os and 5 carbon dioxides. So these are our products. Now we need to kind of further dissect this because pentane has a couple of different types of bonds, and water and carbon dioxide have multiple bonds as well. So when I'm looking at this pentane, first thing I want to do is I want to see how many carbon-carbon bonds we actually have. So if you just want to count them, there's the first one, there's the second one, there's the third one, there's the fourth one. So this first molecule, pentane, has 4 carbon-carbon bonds to it. Now it also has a secondary bond. It also has carbon-hydrogen bonds. So how many are there? Well, since there are 12 hydrogens, there need to be 12 hydrogen-carbon bonds. Those are all the types of bonds we have in this first molecule. In the other questions, you might come up with a molecule that has a triple bond, and then maybe a couple of single bonds. That means that your very first thing you do might have more than 2 types of bonds. It could have up to 3 or even 4. So just be aware of that. Now, as we get over to the oxygen gas, there are 8 of them, and there's really no way to simplify this oxygen gas. It's just one double bond per molecule. So we have 8 of them, so there's 8 of these double bonded oxygens. Let's put the arrow in. Now, when it comes to this water, H2O, we've got oxygen-hydrogen bonds. There are 1, 2 per molecule. You see that? 1, 2. 2 per molecule. We have 6 molecules in total. 2 times 6 is 12. There are 12 OH bonds present here. The same idea applies over here to the carbon dioxide, where we have a couple double bonds. one there, one there. So we have 2 per molecule, 5 molecules in total. 2 times 5 gives us 10 of these things. Next step is you're just going to go to that table that I mentioned earlier, which is there, and we're going to start to fill the bonds in, or fill the terms in. The first one here is a carbon-carbon bond, which is right there. I can read it. It's 346, so I'm going to put that one in. Then we've got a hydrogen-carbon bond. That one is 338, and we have 8 of those double bonds. Remember, the double bonds are right there. In a second, we're going to total up mathematically what all those are equal to. So 4 times 347 plus 12 plus yada yada. We're going to add those up in a moment, but we'll deal with the other side here where we have 12 of these OH bonds. OH is worth 460. And then we have 10 of the OC bonds, and those are worth 745. So back to the math here. We want to figure out how much energy the reactants, the energy total of the reactants, and that's 9428. If we go over to the energy that it takes our products to form, we get 1297. Now we do have this equation here. This will help us figure out if this thing's positive or negative. So we're going to take our equation, or our energy required, and subtract off our energy released. And that's going to be equal to minus 3542 kilojoules per mole. Another way to spot this is just to say that, again, if that's our arrow, we've got that number and we've got that number. Well, it should probably be pretty clear that, this side of our equation here, we've got this much of a difference. So it's like saying we have 3542 on the right side, because 12,000 is bigger than 9,000. So we could represent this here using our potential energy diagram. I'm just putting the numbers in. Again, it appears like we've got more energy, but energy again has been released to the system with that amount of energy being released. And we want to write our equation finally like so. And since it was exothermic, we need to add that number over on this side. Now I keep it as positive. It's positive on this side because it was a reactant. So there's sort of 2 ways to look at this. If I ask for the delta H and the delta H is a negative value, you need to know that is exothermic. We can sort of eliminate that negative simply by writing it on the correct side of our equation as one of our products. Let's take a look at another example where we get something that's endothermic. So determine if the decomposition of water is exo or endo. We don't know. Some of these, like combustion, are always exothermic. This one isn't, well, I don't know. It could be either. So first thing we're going to have to do is write an equation, write a balanced equation. After that, we're going to have to sort of dissect this and say, yeah, we have 2 water molecules, and we've got 2 of these hydrogens. Those have single bonds, and then we've got that oxygen double bond. And then we got to simplify this one a little bit because it has a couple of OH bonds per molecule. 2 times 2 gives us 4 of these OHs. So there's the 4 OHs there. And then these are already simplified, so we just rewrote them here. Table of values here for our terms. So there are all of those values. You can double check them on the table if you so desire to. I've gone ahead and I've added this one up. And hopefully you can see that we have a bigger number on this side. And it should be bigger by 470 kilojoules per mole. So this is, in fact, the value we need to sort of drive this equation. This amount of energy is coming from our surroundings and is going into our system. So we can subtract them here, and now we get a positive value. So that should tell you that when we have more energy on the left side of our equation, we get a positive value for delta H. Here's our diagram. There's our change in energy. And this is endothermic. I like to finish these off by writing my equation and putting that value as one of our reactants. Again, notice in our equations, if you remember back to the earlier slide, both I write as positive values when they're written in an equation. When we're talking about a delta H with a positive value, that means that we're talking about an endothermic term. And that wraps up that.